For over half a century, it was basically the holy grail of physics. A goal so big, so audacious, that a lot of people thought it was just plain impossible to take a direct picture of a single atom. So today we're going to dive into the incredible 60-year human story behind the quest to see the very building blocks of our world.
It's one of those questions that sounds simple, right? Something a kid might ask. But it gets right to the heart of this huge scientific challenge. I mean, if you take any object, let's say a piece of metal, and just keep magnifying it, what do you eventually find? Is there like a final layer to reality?
Okay, let's put this into perspective. To get from our world down to the world of the atom, you need to magnify something about 50 million times. That's the almost unimaginable jump in scale we're talking about here. And this is where that jump takes us. Look at that. Each of those little bright spots you see, that's an individual atom, all lined up in a perfect grid. It's a breathtaking image for sure. But what makes it so powerful is that for most of modern history, the known laws of physics basically said that this picture could never, ever exist. So why? What made it seem so impossible? Well, the problem starts with the very thing we use to see anything at all: light. What's so fascinating here is just how mismatched these two things are. Seriously, imagine trying to read Braille while wearing giant foam fingers. It's kind of the same idea. The waves of visible light are literally thousands of times bigger than a single atom. They just wash right over it without picking up any detail. So to visible light, an atom isn't just small, it's completely invisible. So to see an atom, you're going to need a whole new kind of light, something with a wavelength tiny enough to actually resolve it. And the breakthrough didn't come from some new kind of light, but from totally rethinking what matter itself is. So in 1924, this physicist, Louis de Broglie, just drops a bombshell on the world of physics. He says everything has a wavelength, even tiny particles like electrons. And here's the kicker: the faster you make an electron move, the smaller its wavelength gets. If you accelerate it fast enough, its wavelength becomes tiny, small enough to actually see an atom. And just like that, the impossible started to seem possible. And this is that idea in action. A PhD student named Ernst Ruska actually brought this theory to life back in 1931. The setup is genius, really. You boil electrons off a hot wire, use a huge voltage to shoot them down a tube, and then you use magnetic fields to focus them instead of glass lenses. When that beam hits your sample, it creates a sort of shadow, an electron imprint that becomes your image. The transmission electron microscope, or TEM, was born. Now, the TEM was a total revolution. Right away, it was seeing things no light microscope could ever dream of. But just as scientists were getting closer and closer to that atomic scale, they slammed into a brick wall, a flaw so fundamental it seemed like it was woven into the fabric of physics itself. And it stopped progress dead in its tracks for 60 years. You can see the whole story right here. A few years of absolutely explosive progress, and then nothing. A dead stop. In 1936, a physicist named Otto Scherzer published this mathematical proof that was basically a death sentence for the dream of seeing atoms. He proved that a perfect electron lens wasn't just hard to build, it was physically impossible. And the culprit has a name: spherical aberration. With any simple lens, the light rays that go through the edges get bent more than the ones that go through the middle. So instead of one sharp, single point of focus, you get this smeared out blur. And the more you try to magnify, the worse that blur gets, forever hiding those atomic details you're trying to see. Okay, so here's the crucial point. With light, there is a simple fix. You just add a second lens that bends light the opposite way, a diverging lens, and it cancels out the error. It's how basically every modern camera works. But here's the problem. Scherzer's proof showed that for the magnetic lenses you need for electrons, a diverging lens was impossible. You could only focus the beam, you could never unfocus it in just the right way to fix the blur. And there it is, right from the 1936 proof itself. This wasn't just an opinion. It was presented as a fundamental law of electromagnetism. You simply couldn't build the part you needed to fix the problem. The dream of seeing atoms was officially blocked by a law of physics. The door had been slammed shut. And, this wasn't just some abstract theory. It was a source of real human frustration. Decades later, another giant in the field, Albert Crew, basically said what everyone was thinking. You can just feel the despair of generations of scientists who had tried and failed to get around Scherzer's proof. For all intents and purposes, the problem was unbeatable. So for over half a century, the dream just sits there, dormant, trapped by this one tiny flaw. But what if the proof itself had a hidden loophole? A small, underfunded team of scientists who a lot of people thought were kind of crazy started chasing an idea that sounded like it broke the laws of physics.
Okay, so let's go back to Scherzer's impossible proof for a second. Like any proof, it has to make some assumptions. And buried in all that math was one key condition, that the magnetic lens had to be perfectly round. I mean, it makes sense, right? A perfect lens is supposed to be perfectly symmetrical. That's how you get a clear image.
And this was the huge counterintuitive leap. What if you did the exact opposite of what every lens designer in history has ever done? What if you built an intentionally imperfect lens? Could you actually find the solution you needed inside the very distortion everyone was taught to avoid? And this was their wild three-step plan. First, they used a magnet with 6 poles, a hexapole, to purposely warp the electron beam into this bizarre triangular shape. Then, their calculations showed that inside this distorted mess, there was a tiny region with the exact opposite diverging effect they needed. And finally, they used a second, opposing hexapole to precisely unwarp the beam, which left only that magical corrective force behind. It's genius. But man, this was a fiendishly difficult thing to build. By 1997, after years of struggling, their funding was about to get cut. They had one last shot to prove their crazy idea worked. The first test? A total failure. Defeated, they just let the machine sit overnight. But then, at 2 in the morning, they decided to try just one last time. They flipped the switch, and the blur that had defined the limits of science for 60 years just vanished. And in that quiet, early morning moment, the roadblock that had defined an entire field for 2 generations was just gone. Science had just been given a brand new pair of eyes, and a whole new era of discovery was about to kick off. This is the world that scientists saw for decades. This fuzzy, frustrating landscape where you knew the atoms were there, but you could never truly see them. Their structure, all their secrets, all hidden in the fog of that one single, unavoidable flaw. And this is the world after. The difference isn't just an improvement, it's a complete revelation. We went from a vague hint of atomic structure to a crystal clear map, showing every single atom exactly where it is. The unseeable had finally, beautifully, been seen. So why does all this matter? I mean, it was a complete game changer. For the first time ever, we could see exactly how atoms are arranged in a material and connect that structure directly to its properties. You know, like its strength or how well it conducts electricity. This unlocked a whole new age of material science, leading to better medicines, faster computer chips, stronger metals. We basically stopped just discovering materials and started designing them, atom by atom. You see, this whole 60-year journey, it wasn't just about taking a picture. It was about gaining a new sense, the ability to see and understand our world at its most fundamental level. It gave us the blueprints to reality. And it leaves us with the most exciting question of all. Now that we can finally read the instructions, what are we going to build?